Okay, good morning everybody. Do you hear me well? Okay, my name is Hans Dick. I'm the Geothermal Product Manager in SLB. And my talk is making EGS accessible everywhere. It's a little bit the term that Tony just mentioned. For me, it's a bit of a provoking title because the idea is, indeed, EGS has making a lot of progress in the last few years. But my presentation is divided into two main parts. One, trying to convey what is the status today of EGS, especially focusing in US, who is leading the EGS space today. And then the second part is identifying some of the technical challenges that we believe need to be sorted out in EGS. And obviously we see that as opportunities and things that we're working internally in SLB to help EGS becoming a reality in terms of the scale up. Let's remember that right now, EGS, if we count how much energy we're producing, probably we have a few megawatts that are being produced today in Nevada, okay? So, just very quickly, I think the previous presentation helped me a little bit setting the stage in terms of this is just an illustration of the different geothermal systems. And I wouldn't go into the details, but just wanted to make sure that we have a distinction of each system and its characteristics. And obviously we will be focusing on enhanced geothermal systems. There are some reference here that, again, these are not absolute numbers, but just roughly that give you some idea of the potential. And if you start looking typically for, let's say, heating applications or even power from a sedimentary basin point of view, we talk about, well, even heating, but this is another application, but let's say sedimentary basin, we talk about gigawatt potential. And when we start talking about hydrothermal system, which is the what we call conventional, we still talk about gigawatt potential. But the promise of this geothermal everywhere comes from the potential of, at least from the pure subsurface, we start talking about terawatts when we start talking about EGS and AGS, advanced geothermal systems. So my talk is gonna focus only on EGS. I think very quickly, this is where we create a reservoir. So typically we are drilling into a rock that obviously needs to have a certain temperature, and where we typically will not have natural permeability, or let's say permeability not enough to be commercially viable. And in principle, we don't require reservoir fluid because it's a system where we will be circulating water in principle, but there is some water loss, by the way, in EGS, and this is one of the areas that needs to be understood. How much is the water loss in the long-term circulation of the system? So I'll start talking about what I call unlocking EGS and focusing in the United States case. So here on the left, we have a graph where we show the power capacity that is expected to grow in United States this is a reference every 5 years. And if you see, there's an expectation that there are various studies that have been released by the Department of Energy in the United States where they predict very strong growth in geothermal power capacity. And if you look at the split, most of that growth is coming from EGS. So we can debate if exactly, there are different studies, so these numbers can vary a bit, but there are basically two references that talk about 60 gigawatts by 2050, and another one that actually went all the way to 90 gigawatts. And if we start looking at how much is that out of the total power capacity in US, let's say by 2050, that actually, in terms of pure capacity, it's a fairly low-digit percentage of the total capacity in the United States, let's say projecting by 2050. We're talking about maybe 3, 4, 5%. But when we take into account actually how much I'm generating, that percentage jumps to 8 or 10%, because that's one of the features, the qualities of geothermal. As you know, the capacity factor is much higher in comparison to solar or to wind, okay? So that's a first graph. The second one talks about the technical potential. And again, the point here is to show that, technically speaking, from a subsurface point of view, that's not a restraint in terms of going and generating 60 or 90 gigawatts by 2015. If you see right now, the potential is estimated something in the order of magnitude of 5 terawatts for the United States. So there is plenty of resource. The question is if we can deploy develop it economically. And then the last one is, this is an interesting graph. There was some reference in the previous talk again on the shale revolution, because EGS is using a lot of the book of the US shale revolution in oil and gas. And as you see, we had tremendous performance improvements. I have here just a couple of metrics in terms of, in terms of ROP or in terms of the lift cost. And basically over a decade we had US oil and gas, unconventional oil and gas operators decrease lifting cost by 4, and drilling efficiency was improved by 3. And I mean, again, these are not absolute numbers, but reference in terms of different operators. So something very similar is happening in EGS, as I will show in the next slide. So where is EGS today? Here I'm showing a graph from SLB Energy, who last week they released a paper in the Stanford workshop where they shared with the industry where they stand in terms of drilling performance in their most recent wells. So if you see here, this is a graph of their most recent wells, and we have here the cost per foot. So this is primarily drilling, a drilling cost reference. And obviously here on the right we have the days per well. And if you see, there has been a tremendous performance improvement. I mean, this is well by well. So this is a tremendous learning curve. I wish this is something we could demonstrate in any drilling campaign, having this much rapid improvement well by well. But definitely what we're seeing is that the cost is sort of going into the $400 per foot, which actually is a cost very competitive with what today any unconventional oil and gas operator is doing in Permian, for example, and probably the biggest, most prolific oil and gas unconventional basin in the United States. So definitely tremendous progress on the drilling performance. And this is more from last year, as here we're showing a little bit of the history of different EGS projects and what sort of flow rates they achieved. This is in barrels per day. Maybe from a geothermal point of view, we're more used to on liters per second. But just as a reference, the flow rates that they achieved during their 37-day well test they performed last year, where they managed a peak of about 63 liters per second, something in the order of 34,000 barrels per day. So I think this is showing obviously the flow rates that perhaps not yet the amount of flow rate that you're expecting for an EGS system. Typically the reference is more in the order of 80, 100, 120 liters per second. Let's say at least 50,000 barrels per day, but definitely in the right direction. And obviously this is where some of these latest wells are going for longer laterals. I suppose that this implies that they're going to have potentially going to do more fracs so that they would be able to increase these flow rates. Any questions so far? So if we start looking at the LCOE, the levelized cost of energy, and this is taking Lazard as reference. This is the cost per megawatt hour. This was initial DOE, the Department of Energy estimate in those reports that they released in 2019 and in 2021, where they estimated that the cost for EGS was sitting in the order of $450 to $500 per megawatt hour. Then we have in the bottom the cost that a conventional geothermal system and subsidized, they're in the order of 60 to 100, and then if you take into account subsidies, the cost is more in the 37 to 87. This is for geothermal systems. And obviously I didn't include here, but as you may know from Lazard, you have the cost of other energy sources as a reference, and geothermal, which is conventional, is competitive. For example, if we start comparing with solar plus battery storage, or the same applies with wind because they are intermittent. So the point is that based on some of the reference we hear in terms of improvement of drilling performance, etc. If we take something in the order of 70 to 80% reduction of those costs that have been achieved, EGS today is probably sitting in the order of 100 to 150. And if you see, obviously that number is starting to approach very much the numbers of what would be conventional. So I think in given as a reference, the USDOE is those same reports that I've been making reference. They've been talking about achieving $45 per megawatt hour by 2050. And they brought that to US dollars in 2019. And they have some intermediate targets set for 2035. And the main message here is that what we're seeing today is already ahead, and definitely, at least in terms of drilling performance, of what was expected to, as those targets that were set back for 2035. So the performance that we're seeing already today, and as was confirmed by the previous presentation, have been tremendous to the point that we're ahead of the curve. You have a question?
Yes. No, I wanted to understand. Obviously, you know, when you give a range, just like for conventional, you're putting together many things, right? You know, there are big plants, small plants. Okay, sorry. Thank you. So I was saying that obviously when you put a range, you're putting together many different things, like small plants, big plants, high enthalpy, low enthalpy, whatever, right? So I was wondering, when you estimate an LCOE for EGS, that EGS can be very different things, right? It can be many different kind of designs, let's say, of the system. So what is the basis for that? I mean, what kind of EGS activities are foreseen in that levelized cost of energy?
So this is primarily taking the design that is being deployed today in US, which is it's a horizontal well. From initially 3,000 foot lateral, they're going into 5,000 foot lateral, cemented casing and plug and perf. And obviously there is a very easy comparison to the performance from unconventional oil and gas, because it's very similar to a certain extent. Obviously those wells tend to be longer laterals, but there is a reference in terms of cost per well, which allows you to have better idea on where the cost sits today. If you saw from the previous slide, and probably the first well that was drilled was over 70 days, and that was probably not even one of the horizontals, one of the monitoring wells that they drilled horizontally. Today they're drilling, I think it was the last well was in something in the order of 20 plus days, 21, 20, okay? So tremendous performance. And if we look at Forge, they've shown a similar, I think their curve is more on bottom hours, but again, you see a fourfold improvement in terms of drilling times. So the other is then, if we think about energy output, the systems today with some of the laterals that they're targeting 5 to 10 megawatts seems to be achievable. Let's assume let's take into account the correlation from that flow rate that I showed in the previous slide was a 3.5 megawatt estimated, and we're talking about wells on a length of approximately 4 kilometers. Typically, I think they're drilling 13,000 feet today. So again, competitive. I think it starts being competitive if drilling those wells and completing those wells starts being is able to achieve similar costs as oil and gas.
So Hans, have you looked at what the impact of additional 10 degrees centigrade is if this lateral was 10 degrees hotter? Have you looked at the impact of that?
I have a slide towards the end that talks about total system performance, and although maybe I won't be able to tell you, I think it's a good slide to have that. Can you part of that.
Absolutely. Yeah.
So I guess now I'm going to start going into the second part of my presentation, which is, okay, what are the challenges that we think we have today that need to be sorted out for EGS to become a reality? And when I talk about reality, is obviously becoming a massive scale-up option in terms of the decarbonization, and becoming if we look at today, at least in US and worldwide, geothermal is, on the power side, is definitely less than 0.5% of the total power generation in the world. So definitely, let's say we start talking about geothermal power becoming, as a minimum, starts becoming a single-digit percentage of the, hopefully, as maybe we were seeing from the previous presentation, it goes into the double digits. So on the drilling efficiency, again, we're talking about getting to the point where we get to this economic target, and I think this is one of the areas where we have seen the most improvement. Very similar to a previous presentation, I think there were a lot of similarities. We're talking about ROP and durability. I think today nobody doubts, and granite, I agree, talking about a single bit run to drill this entire lateral is not an utopia, or I don't know if that's the correct term in English anymore. No, I mean, probably the last well was drilled already in 3 bit runs, and we look at last year or 2 years ago, we're talking about dozens of bit runs still for the very first wells drilled in EGS. So tremendous improvement. Definitely, maybe 2 years making that statement would have been a bit of a challenge, but today nobody doubts it. There is an element of well placement and trajectory. I think we touched on that already a bit. The tortuosity of these wells, which have been drilled for the most part with motor, the tortuosity that kind of BHA generates has some implications in terms of, for example, the completion or the fraction initiation. So there are some opportunities definitely on that side. And there is a challenge of geothermal, and this is a problem for hydrothermal and for EGS, and it's fit for purpose technologies. A lot of times we have the technology already available in oil and gas, but it's not economically viable for the returns that you have in geothermal. When we start comparing returns from geothermal versus oil and gas, there is at least one order of magnitude in terms of the value. And a lot of times we've been talking about when we show or talk about levelized cost of energy, that's one reference, but we need to start talking more about the value that geothermal brings as an energy when comparing with other energy sources, because that's where maybe the equation starts helping geothermal business case. So in terms of bits technology, I just do a quick summary in some of the things we've been doing in recent years. So we specifically launched a PDC bit that is specifically for this type of environments. It has, I think it's very similar to what was described before, cutters that are able to handle better, they are thermally resistant to this kind of environments in terms of the temperature that they will see, and allowing that cutter to remain to be able to withstand longer, because the moment that cutter starts deteriorating, degrading, that very quickly goes south, and then you pull out the bit and the bit is completely wrung out. But actually, if you can avoid that initial degradation of the cutter, that's where the bit can actually last much longer. So the other thing we've been working is on rock cut modeling with Utah Forge. I have a reference at the end of the paper we co-authored last year, and we're continuing, and I guess jumping a little bit into the challenges. We need to keep improving performance. I mean, as I said, the goal of 1 bit run and keep improving that ROP is there. I think it's very attainable in the medium term, but I think we're starting to see the need for EGS to start going for longer laterals, for bigger wellbores potentially, because today probably we're doing 8.5 open hole with a 7-inch production casing. But we're starting to think about what if I do a 12.25 because, or at least a bigger wellbore, because I need higher flow rates and potentially as well high temperatures, right? So this is what do I do? And we'll talk a little bit about later on. Some of the things we're working on forward is continuing our modeling of the rock cutting, and we think that a better understanding of that modeling will allow us to do better designs going forward. And obviously we're working, as any bit company, we're working on next generation cutters. I have a slide on the high temperature. I think it's important to discuss a little bit of what we see in terms of temperature management. And this is a reference, this is actually a slide from a hydrothermal system. But I think if we model to a certain extent, we would see similar results for EGS. And actually it's been published, so we can also look at some of those. But here what I have is depth, obviously, and here we have temperature on the x-axis. In this light blue we have the temperature, the static temperature that we're measuring. And then here we have a series of wells that we're drilling. This is the circulating temperature. The actual temperature we're circulating through the BHA, reflecting the temperature at the bottom of the BHA as we were drilling. And what we see is that typically the means that we've deployed for decades in terms of mud cooler, and I think in EGS sometimes we're starting to consider, in some cases, using insulated roll pipe. But if you see, we are able to drill with current technology that is typically rated to 150 degrees Celsius. We can drill geothermal wells. And if we go to Indonesia or Philippines or New Zealand, I think, or US, we will see this is more or less what any geothermal developer today does. They don't require, in principle, any special technology for higher temperature to drill these wells. I think what we need to take into account, I think rightly said in the previous presentation, is we need to start challenging the status quo, and maybe there are other ways to drill those wells that actually depart from the mud cooler, and actually start looking at, okay, what if I do an offset of, it's a cost-benefit analysis. And it doesn't have to be a mud cooler, but it's fairly efficient from a cost point of view, and we need to, if we're gonna challenge that, we need to come up with something that can be competitive. The other point to make here is, obviously if we start drilling longer laterals, and especially in EGS is going to be, I think, the case until we find that sweet spot, how long does the well need to be efficient and produce enough power or efficiently, is okay, what's going to be, then I think we'll start seeing, if we go for longer laterals, we'll start seeing higher temperatures, and then we might start needing to go for special technology can handle temperatures above 150. But if you see here, we're drilling, this is 250 degrees, which is typically from Indonesia or some of these, I mean, these are the typical environments that we drill in some of the hydrothermal systems, and the gap is huge. I think we can manage. There is some risk associated. Obviously, if I get stuck, I might fry my tools, for sure, but for the most part, I think can be done. The next one is on cementing technology. So again, this is, it's a bit of, I guess, a marketing slide, but the point here is that there is existing technology today that if you look at, particularly in this case, Thermostone, it's a cement that we developed actually quite a few years ago. It has high coefficient of thermal expansion, which basically means that we can handle not only high temperatures. If you look at here, we're talking about 350 degrees Celsius, but it can also handle the changes of temperature and pressure that you will see when producing a geothermal well. It has a low junk modulus, which is also convenient. It has been used a lot in SAGD applications, and actually last year we cemented the last well that was drilled by Utah Forge with Thermostone. So definitely, I think this is where demonstrating the value of properly cementing a well in an industry where typically is very challenged from an economical point of view, it's difficult. I think we have struggled in the geothermal industry to demonstrate the value of this type of technologies and the value that it has in the long term, in the well integrity long term. So if you go to a geothermal operator and you try to, especially in hydrothermal systems where you typically will have losses, and you try to make a case of the importance of cement and being able to withstand a long-term longevity of the well, avoiding a casing collapse, as Tony was mentioning in the previous presentation, it is a challenge. I think this is where sometimes the developers tend to cut corners, unfortunately, and then prefer to leave the problem for later. Okay. So the next one is the point around effective heat extraction. So obviously, when we are talking about EGS, we're aiming to maximize the surface and volume exchange that you are creating between these two wells. You need to maximize that in connectivity, meaning that you're obviously aiming to have as much flow rate, and that implies that, for example, if you go for a plug and perf, you want to get as even distribution of those flow rates among the different frac stages that you have performed, and you want to maximize the residency time. That means the time that fluid is transiting from one well to the other. Otherwise, basically this is obviously associated with the heat transfer you're going to get. So that's why we talk about flow distribution, and these are clearly more on the long-term production of these systems essential, because you don't want, for example, to start seeing a rapid temperature decline, or the fact that maybe one of the frac stages pretty much short circuits the flow, so that then you are not getting the amount of heat transfer that you get, because primarily one frac becomes the primary path of least resistance, and then you're not getting the power output that you require. So some of the things that we're working on this front is in terms of fracture characterization. One is in terms of logging, being able to log in high temperature environments. If we look at Forge or Fervo, those are systems that are, Fervo previously was in the order of 190 degrees Celsius. I think now they're drilling more into 200. And Forge was a bit hotter. It was more in the 220 degrees Celsius. So the fact that these wells are deviated when you need to log is not, obviously not straightforward. And the main mechanism that we have been utilizing is the through-bit solution. So basically, this allows you to quench the well. So basically, circulate the well. Once you drill to TD, you pull out. Obviously, you do a good circulation to cool the well. But then once you go back in with the logging tools, you are able to circulate, keep cooling the well as much as you can, and then you are going to actually perform. You open a window that allows you to log the well. The next one is, here I have some examples in terms of fracture characterization, which is extremely important in hydrothermal systems, but as well in EGS, although in principle you would say, okay, but I'm drilling into rock where I'm not expecting to encounter the natural permeability, but the reality is in some cases you might induce fractures, as we were seeing when you're circulating cold fluid. There is some effects of thermally induced fractures that you are able to do, and you also want to identify the natural fractures. So there is an interesting paper, very good paper that we presented last year for geothermal rising, where we show that characterization, the process of the interpretation of the FMI in combination with the OBI, and then how it matches very well with, in some cases, when we had the cores accessible. So if you see here, there is the readings from FMI. Maybe the level of detail is not very good. In some cases, you might have overinterpretation of certain fractures, but with the OBI, you are able to actually refine that, and it matches very well with the actual core. In some cases, also, you are able to differentiate natural fractures from artificially induced fractures. And again, you want to understand, this is extremely important when you start going into your understanding of the fracture characterization from the entire system and not from only well. So the idea is you start obviously going from one well you start expanding that. You start going far field from the well to the point where you have a better understanding of the frac system in your field, and then you can also do a better design of the fracs that you're going to perform on that lateral. Next one is, let me see what happened here. Okay, it's here. So next one is the fracture network modeling. And again, this is not clearly an area of expertise of mine, but what I've seen in the industry is that there is a bit of I would say a healthy debate in terms of if the fracture propagation that you generate when you're fracking these wells, is it predominantly dominant in terms of planar, or there is a combination of non-planar in the way you would model. So here we have an example of the 3 fracs that were performed for Utah Forge. And what I see is that there are different opinions still in the industry. And I think, as I would call it, the jury is still out. So from our perspective, what we see is that we have the unconventional fracturing modeling that we developed for unconventional. We believe that it can bring significant value, and what we're working is, in collaboration with Utah Forge, is to use the existing data, and actually they're going to go also for a new frac campaign, to see the existing modeling with adjustments we need to do for this particular environment, to be able to better predict how these fractures would propagate. So that's one initiative. The other point is definitely if microseismic monitoring interpretation is crucial. You may know that in the systems typically you are running a series of monitoring devices like fiber optics. We think that we're trying to see how we can better characterize natural fractures without necessarily having all the wells in the system. So one thing we're looking at is single well mapping, which means that we might use a source on surface and then use an existing well to on the receiver end to be able to identify natural fractures without having maybe multiple wells. So the other point we're working on is high temperature fiber geophones. So this is something actually, again, we had developed some prototypes some time ago for oil and gas. It never really had an application, and now we see that this has a lot of application for EGS. And now starting to go into production sustainability, system performance, and going back to your question. So some of the challenges that we see is fracture integrity. I think you touched on that a little bit when talking about if we start going for higher temperatures, what are those fractures going to remain open? And I think we need to do quite a bit of homework on that front. Induced seismicity prevention, definitely. And I think a big question is what is going to be the modeling of that reservoir temperature over time? And what's going to be the decline of that temperature? And be able to model that with a fair amount of certainty. So when we start looking at system performance, I think the ability to be able to optimize the heat transfer and that production sustainability I was talking before is extremely important, and how you can optimize system and well design. And a little bit to Tony's question, should I drill to a certain depth with a big bore, like 12¼ or maybe should I drill a little bit deeper and maybe in an 8.5 hole? What is better? Should I extend the lateral maybe 1,000 or 2,000 feet more, or should I keep it? How many fracs should I do? What distance? What's the separation between the producer and the injector well? And I mean, we can go on and on. So this is where I think there is this is where the importance of being able to model not only the subsurface, but then connect that to the wellbore and to the surface is extremely important. So here, some of the things we're working on is better understanding of fracture propagation monitoring. Here we see some interpretation of microseismic observations we did for Utah Forge, and where actually we see, or let's say, some of the tests that we simulated seem to indicate that actually the natural fractures that you may have in some of these systems are relevant for the fracture propagation. So that's one. At least we have some lead that tends to think that it is important natural fracture network, and how that would the implication that would have for fracture propagation when you're modeling that or you're designing your frac stages. We're also working on the microseismic monitoring and how to combine that with deep EM, electromagnetic monitoring. So again, these are things that are already, I think it's not so much on the actual tools that are being used, but how to extract more value out of those. And the last point is, one of the last points I want to make is on coupling. What would be, I think we're all used to, we know that typically you develop a static model that you start, I mean here, these are the systems, the platforms that you use. So we use typically Petrel to have our static model. We combine that with Visage. That's something that we do today. So we are able to combine the mechanics associated with that subsurface. But we're looking into doing a fully coupled model that basically allows us to understand the implications of stress, of fracture propagation, of geochemistry, of temperature, the effects of temperature, flow rates, etc. So this is thermal mechanical coupled modeling. It's not something new, but I think we have only bits and pieces in the industry, and we're definitely think that this is of critical importance for us to be able to start designing the entire system. So we're working on it. I think we already have most of the pieces, because we already have Petrel, Visage, Kinetics, which is the platform we use for fracture design, and we're combining this with Intersect, which is our reservoir engineering platform. And then I think the next piece is integrate this with the wellbore and surface. So we're working, this is an example of a power plant design that we use with symmetry, that again we're coupling with the rest of the models, and start doing full asset modeling. So I think the ultimate goal, now going back to your question, is how can I design my well architecture, start working on different lateral lengths, frac stages, distance between wells. Obviously, do I go for a bigger wellbore or not? Temperature decline, and etc. I mean, this has many.
The key is to sort of really understand the sensitivities, you know, between different things here. You know,
definitely.
If I go 10 degrees hotter, am I bringing more benefit than going 2 inches larger diameter, and combinations of that?
Yes, and for example, should I go for a bigger distance between wells, but I'm going to ensure I'm going to get the connectivity between those two wells when I frac them and so forth. So I think there are various elements, because maybe temperature decline is an issue. So maybe I need to go for a larger distance between wells, but maybe then I start affecting the connectivity.
That's really good stuff, because I think the biggest danger is a shortcut. In the EGS one. Yeah.
Yes, and I think for now what we see is that there is no specific. I mean, there's a question if we should start developing a completion mechanism that allows me to regulate those flow rates across the different stages. I think for now we don't see that being deployed, but it's definitely in the heads of everybody.
Yeah, that's really good for me, because that's another technological boundary that we have to push up temperature-wise. Yeah?
Yes, definitely. And I think with that, I mean, I'm just summarizing the table of the technical challenges that we see, and what opportunities we're working on to aid and support the development of EGS in the short, medium, and long term. So that's it for me. I don't know if any questions, but thank you.